Good morning, welcome to the Lionheart Academy. We're on our trigonometry lesson series. Today is lesson number 59. We're in part 3 of our complex number series. We talked about, in the previous two videos, we talked about what is a complex number, and we talked about how to use polar form of complex numbers to multiply and divide. Today we're going to take a look at how to take powers and roots of complex numbers in polar form. Okay, so we're going to take a look at powers and the roots of complex number in polar form. It is much more efficient, or I wouldn't say easy, but it's a little bit more efficient to take powers and roots using polar forms. And we're going to introduce a theory called the Moivre Theorem, a French mathematician. Alright, so remember, if you want to do z1 times z2, right, is equal to r1 r2 cis theta 1 plus theta 2. So this is the basic rule for multiplication when we want to do multiplication product of two complex numbers. When we want to find products of two complex numbers, CIS again is cosine theta plus I sine theta. Okay, this is theta. So if we want to go ahead and think about this, if you want to go ahead and square itself, well, what does z1 square equal to? z1 square is simply z1 times z1, right? So it will be r1 times r1 by using this rule, CIS theta 1 plus theta 1. So this will simplify to r1 to the second power CIS 2 theta, okay, 1. Because z1. Now what do you think z1 cubed would be? Okay, if we extend this reasoning, it will be z1 times z1 times z1. So eventually this will be r1 times r1 times r1 CIS theta 1 plus theta 1 plus theta 1. So there should be 3 of them. So it will be r1 to the third power CIS 3 theta 1. Okay, so as you can see, if we can continue to develop this logic, and then that means when we do z to the n power, it will be equal to, okay, r, let me go ahead and write it like this, cosine theta plus I sine theta. We are raising this whole complex number to the n power, and this will be r to the n power times cosine n theta plus sine n theta. Okay, so this is another way to write this, is r to the n power CIS n theta. Okay, so this will be an important formula that we will need to use. Okay, and we call this the Moivre theorem. He was a French mathematician, the Moivre theorem. So this is basically saying the nth power of a complex number is a complex number whose modulus is the nth power of the modulus of the given number, and whose amplitude is n times the amplitude of the given number. So the modulus, as you can see, is being raised to the n power, and the amplitude, or the argument, is being multiplied by the n power, multiplied by n, okay, rather than raised to the power. Alright, so let's go ahead and take a look at an example here. So this is a very straightforward formula. Let's go and try to find square root 2 plus I square root 2 to the 4th power. Now, this complex number is in rectangular form. We could go ahead and do this by multiplying this by itself 4 times, and it's possible you can do it if you're good with multiplication and using distributive property. There's no problem, you can do it. But let's not do that using the rectangular form. Let's go ahead and do this using the polar form, and let's see what happens. So let's go and find out what is r. So r is square root 2 square plus square root 2 square. Okay, so it will be 2 plus 2 square root 4 square root 4, and that will be 2. So the radius is 2. The modulus is 2, or the absolute value. Alright, let's go and find out theta. Now, I'm looking at this, x value is positive, y value is also positive, so that means it's in first quadrant, so I don't need to worry about adjusting the angles. So square root 2 over square root 2, which is 1, okay, arctangent of 1, which will be give us 45 degrees. So this modulus is 2, and argument or the amplitude is 45 degrees. Okay, so what we're doing here is we're doing to CIS 45 degrees. We're raising this number to the 4th power. Okay, we're raising this number to the 4th power. Alright, so if we raise this number to the 4th power by using the rule, by using the Moivre Theorem, we have to say it's going to be equal to 2 to the 4th power. CIS 4 times 45 degrees. Okay, so 2 to the 4th power is 16, and 4 times 45 degrees is 180 degrees. Okay, CIS 180 degrees. So this is the polar form of the answer, and we could convert this back to the to the rectangular form. Okay, so this is 16 cosine 180, right, plus I sine 180 degrees. Okay, this is the rectangular form, and this would be 16 cosine 180 is -1, I sine 180. Now sine 180 is 0, so 0 times I is still 0. So this is simply a -16. So the 4th power of this number square root 2 plus I square root 2 is equal to -16, or 16 CIS 180. Okay, so you can express this graphically. Okay, I just want to show you where it's graphically. It's right here, -16. Alright, so this number is 16 180 degrees. Okay, why is that? Because radius 16 and the angle is 180 degrees, right? 180 degrees. As you can see, this is 16. This distance is 16. So, but the rectangular form, this point is -16 0. Polar form is going to be 16 180. Okay. All right. So let's try another example here. All right. So now, what about the cube root? Let's go ahead and find root, cube root, or possible root, or any kind of root. Okay. Well, how do we express roots, cube roots, or any kind of roots? If we want to go ahead and express roots, alright, let's go ahead and find this example I'll show you. Remember, a square root of x is simply x to the 1/2 power. Okay, now usually we don't put a 2 here for square root. A cube root of x is simply x to the 1/3 power. So when we can express roots as exponential expression. So nth root is simply x to the 1 over 1 to the x to the 1 over n power. So this is how we're going to express roots. Alright, so this is something that we have to remember from before. Alright, so we want to find the cube root of -4 plus 4i cubed to square root 3. So let's go ahead and find r and theta first. Okay, let's find the modulus. So it's -4 square plus 4 square root 3 square. Now remember, it's hard to find the roots, especially hard to find the roots using rectangular form. So we want to use the Moivre Theorem to help us. Now, so this is square root of 16 plus 16 times 3 is 30. 16 times 3 is 48. So it's square root of 64, and that will give us 8. Okay, so modulus is 8. Now what about the angle here? Now this is in a second quadrant because x is negative, y is positive. So when we do arctangent 4 square root 3 y over x, I am going to add 180 degrees to it. Okay, so let's see. This is square root 3 over, so it's basically square root 3 over 1. So it should be equal to a -60 degrees. -60 degrees plus 180 should be 120 degrees. Yep, 120 degrees. Okay, should be 120 degrees. It's in second quadrant. So that means we are finding the cube root. Okay, cube root. That means we're finding 8 cosine of 120. Alright, okay, cosine 120 degrees plus I sine of 120 degrees. Okay, so basically we're taking this complex number raised to the 1/3 power. So another way to write this is a CIS 120. Okay, I'm just gonna do that 1 over to the 1/3 power. Alright, so when we raise to the 1/3 power, this is basically finding the cube root. Okay, alright. Now, The thing is about finding the cube root of this thing is we are actually having a little issue here, because when we find cube roots, right, we usually have 3 roots. In complex number, we should have 3 roots. When we find square roots, we should have 2 roots. And when we find fourth root, we should have 4 roots. So when we find cube roots, we should expect 3 roots. But here, when we use a cos CIS 120 and raised to 1/3 power, we will only have one answer. So what happens is that we need to have, besides a CIS 120, we need to have 3 other coterminal angle, 3 other numbers, expressions of the same number, but using coterminal angles. So 120 plus 360, the next angle is 480, okay, and the next angle is 360, that will be 840. So these three angles are all coterminal angles. So here, ACIS 120, ACIS 480, and ACIS 840, they are all the same number, but they have different amplitude, they have different arguments. Okay, they all have the same radius. Oops, couldn't draw a straight one. Okay, so it's like they also have the same radius, 8. Okay, and they all have the same reference angle in the second quadrant in a sense, so it's the same complex number. But why do we have to have 3? Because we have to have 3 roots. And so basically, this is something that you have to remember, is whenever we take roots, we have to have that number amount of roots. And then in order to have that number amount of roots, we have the equivalent numbers first, and then once we have that distinct numbers of distinct numbers, and we can find the distinct number of roots. Okay, so every complex number except 0 has n and only n distinct nth roots. So that's a very key concept. Okay, every complex number has, except 0, of course, has n and n distinct roots. So therefore, we have to have n number of equivalent numbers, so for us to take roots with. Okay, so hopefully that explains a little bit. Okay, and then alright, so let's go ahead and do the mathematical ones. Therefore, every time you take roots, you need to remember to go ahead and get at least that amount, and we need to get, and if we're taking nth root, we need to have n distinct roots. So if we're taking cube root, we need to have 3 roots. Alright, so instead of ACIS 120 degrees, we have to use 3 of the equivalent. We have to use 2 more, okay, including the CIS 120. We have to use the equivalent coterminal angles to get the equivalent complex numbers and to take the root of each one of them. Alright, now you will see that after we take the cube root, all 3 of them will be within this, the first cycle. They will not be coterminal anymore. So let's go ahead and take a look at that. So it's going to be a to the 1/3 power CIS 1/3 times 120 degree. Okay, so this will be 2 CIS 60 degrees. Okay, I'm sorry, 40. 120 divided by 3 is 40. Okay, alright, so here the second one is ACIS 1/3 times 480. So it's 480 divided by 3. So it will be 2 CIS 160 degrees. As you can see, they're not coterminal anymore. And a 1/3, a to the 1/3 power CIS 1/3 times 280. Not what 280. I'm sorry, 840. Okay, so it's going to be 2 CIS 280. Yes. After you divide, it's going to be 280. So those are the 3 answers, 3 roots, distinct roots for the cube root of -4 plus 4i squared 3. So this is a very important part that we need to understand. Okay. All right. Now one last example here. So let's say we want to solve the equation x to the 5th power minus 1 equal to 0. Okay. So if you want to solve for x. Now, I know this, of course, you would say, yeah, x is just equal to 1. That's true, x is equal to 1. But in complex numbers, there will be 5 roots. So x to the 5th power is equal to 1. So basically, we want to, what this means, we are solving for, we are finding the 5th root of 1. Okay? Now, 1 is a rectangular form. Now, what does 1 look like in polar form? Well, the radius is, well, if I go ahead and graph this, 1, right? 1 is right here. So the radius is just 1. And what about the angle? So looking at this picture, I can see 1 has a degree of 0 degree. So this number can be represented as 1 CIS 0 degree, okay? So that's 1 CIS 0 degree. Alright, now because we want to look for the fifth root, so we need to have 5 distinct roots. So 1 CIS 0 can only give us one root, so I need to have the coterminal angle. And coterminal for 0 is just 360, the next one is 720, the next one is 1080, the next one is 1440. Okay, so we need to have all 5 of them, and we need to take the fifth root of every one of them. Okay, so we're taking the fifth root of every one of them. So the fifth root of 1 is just 1 to the 5th power, and then 1/5 times 0 degree is still 0, so it's 1 CIS 0. So that agree with our real number solution. This is a real number solution. It's just that fifth root of 1 is 1. That's true. But guess what? We have other numbers here. 1/5 times 360 degrees. So that will give us 1 CIS 72 degrees. So that definitely is not a real number, okay? And so here we're going to divide 720 by 5. It's going to give us 144 degrees. Here we're going to divide by 1080 by 5. That will give us 216 degrees. And the last one will give us 288 degrees. So as you can see, they are all, these two, they are all complex numbers. And then, alright, so we are going to go ahead and do some more examples next time, and then, well, we have pretty much done everything that we need to do in complex numbers. We just need to do some more examples and practice. Well, if you have any questions and comments, please go ahead and leave it in the comment sections. Hopefully we'll see you next time. Thank you.